Deductive reasoning, so creating our proofs. Remember, an argument will be valid if and only if it takes a form where it's impossible for all the premises to be true and then the conclusion is false. The ways we do it. The first way, which you have seen, is what's called a direct proof, or to give it its correct name, modus ponens. Using the language of logic, this is basically a direct proof. Remember we said P implies Q meant that if we have P, then we must have Q. So what this is saying is, well, if we've got the situation where we know P implies Q and we have P, then we can logically imply we've got Q. That's what that's basically saying. I'm going to use a truth table to prove that that is true in every single situation. So there are all the possibilities, so true, 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 false, false, true, and false, false. If I push them across into underneath the P's and the Q's. Okay, working inside out of the parentheses there. P implies Q. Well, we said the only one that is false in that one was true implies false. So okay, we've got a value for that. So now I'm going to get these blue ones and go, and the P. We've now got the case where only one of them's true up the top, where we had true and true. And then the last one, bingo. All four of them turn out to be true. If I now take the green one with the Q, every one of those situations would be true. Okay? So that's a nice little way of saying, hey, this is a solid proof. This then is how we structure our geometrical proofs and all proofs for that matter. Because what this is really saying is, hey, if you know P implies Q, but you also know Q implies R, then it's fair enough to say P implies R. Okay, let's do a couple. We're going to prove that if a number is odd, then its square is also odd. So I need a number. Well, let's just call it n. But I want it to be an odd integer. So to force it to be odd, I need to define it. I'm going to call it 2k plus 1. I guess I could have just as easily called it 2k minus 1. But that would force it to be odd. I need to define what k is. K belongs to the set of integers. Well, let's square it. And I want to show that this will also end up in the form of an odd number. N squared will be 2k plus 1 squared. Expand it out, and I can group it in such a way that I do end up with 2 times some factor plus 1. And that factor, 2k squared plus 2k, must be an integer, because we know k is an integer. We find k to be an integer. When I square an integer, I get an integer. When I multiply by an integer, I get an integer. When I add an integer with an integer, p's got to be an integer. So yeah, if n is odd, then n squared is also odd. Here's one from an HSC a couple of years ago. This time we're going to prove that 2 to the power of n plus 3 to the power of n cannot equal 5 to the power of n for integers bigger than or equal to 2. So 5 to the power of n. Well, 2 and 3 are the interesting numbers there. I could rewrite 5 as 2 plus 3. So 2 plus 3 to the power of n. This I could expand out using my binomial theorem. So nc0 2 to the power of n, nc1 2 to the power of n minus 1 times 3, and so on and so on and so on. The last term being ncn 3 to the power of n. Now I know nc0 is 1. And I know NCN is also 1. So basically I must have something there that is bigger than 2 to the power of n plus 3 to the power of n, because of all those middle terms. But of course that would only be true if n is 2 or more. Because if it was equal to 1, then I wouldn't have all those middle terms. I'd only have 2 plus 3, which is actually equal to 5. And of course if I had 0, well, anything to the power of 0 is 1. So that's why I need to say, well, yeah, but that'll be true if n is greater than or equal to 2. Well, if it's always greater than, well, it can't equal it. So there's my proof. Prove the sum of the squares of 5 consecutive integers is always divisible by 5. This is, I want to say trivial, but it's the basic idea of divisibility, isn't it? If p and q are integers, and we know q is divisible by p, then there must exist another integer such that q is equal to p times n. I'm going to let q equal the sum of 5 integers squared. Now I could have gone n squared, n plus 1 squared, n plus 2 squared, and so on and so on. But for this one it's smarter to take advantage of symmetry. So I'm actually going to call the middle term n squared, because I know that when I expand my perfect squares out, now the n minus 1 squared and the n plus 1 squared, that middle term will cancel out. And similarly with the n minus 2 squared and the n plus 2 squared. So it's just going to save me time on the expansion. So I'll end up with, well, each one of those will produce an n squared, so I've got 5n squared. The first one will get me 2 squared, the next one 1 squared, then another 1 squared, and then another 2 squared, and that's 5n squared plus 10. I can factorise 5 out and write it in the form where, yes, this is 5 times something, and that has to be an integer because we defined n to be an integer. So we have our proof. So those are direct proofs. Let's now play with the idea of contrapositives. So we're going to do what's called proof by contraposition, or to give it its correct name, modus tollens. Remember we said this. These are logically equivalent. Not Q implying not P is the same as saying P implies Q. Because sometimes it's just easier to prove it the other way. Certainly with prime numbers. Because it's a lot easier to show something is not a prime number sometimes than it is to show something is prime. We're going to prove that if 2 to the power of n minus 1 is prime, then n must be prime, and n belongs to the natural numbers here. Okay, let's now define it. The contrapositive of this would be, if n is not a prime number, then 2 to the power of n minus 1 is not a prime number. So I'm now setting this up so that n is not a prime number. In other words, I can write it as 2 factors, neither of which is 1. So if I can do that, then it's not a prime number. That's what I'm basically saying. N is not prime. Of course, another way you could have said natural numbers, we're basically saying the counting numbers are the positive integers, and you could say z plus. I'm sticking with n because that's what was in the question, but it's the same as saying positive integers. 2 to the power of n minus 1 then becomes 2 to the power of pq minus 1. Play with my indices. That's 2 to the power of p to the power of q minus 1. But we have a factorisation for a to the power of n minus b to the power of n. So I'm going to use that idea. This would be 2 to the power of p minus 1 in the first factor. The second factor then would be, although I've written it backwards, it would be 1 plus 2 to the power of p plus 2 to the power of 2p plus and so on and so on and so on. And the last one there being 2 to the power of q minus 1 times p. So I've got these 2 factors. Can I now show that neither of those could be 1? It certainly is p times q. Now p is 2 to the power of p minus 1. That can't equal 1 because of the way I've defined things. Remember, I've said p is not equal to 1. Therefore, this is not 2 minus 1. So it can't be 1. Q is 1 plus all of these things, and all of those things are going to be positive numbers. So it's 1 plus something. So Q can't equal 1. So there it is. If n is not prime, then 2 to the power of n minus 1 is not prime. And so now I can say, well then, that means if 2 to the power of n minus 1 is prime, then n is prime by contraposition. So we write down. That's the technique I've used here. This one appeared a couple of years ago. Prove that for all integers n, with n being greater than or equal to 3, with 2 to the power of n minus 1 being prime, then n can't be an even number. Can't be an even number. Again, I'm going to do it by contraposition. So I'm going to let n be an even number, greater than or equal to 3. So n will equal 2 times k, where k is some integer, but my integer now has to be greater than or equal to 2, because I want an even number greater than or equal to 3, and the first even number greater than or equal to 3 is 4. So my k would have to be greater than or equal to 2. 2 to the power of n minus 1, let's have a look at that. That becomes 2 to the power of 2k minus 1. That's the difference of 2 squares. It'll be 2 to the power of k minus 1, 2 to the power of k plus 1. I certainly know 2 to the power of k plus 1 has to be bigger than 2 to the power of k minus 1. Now if I'm trying to show neither of these could be 1, all I've got to do is show that the smaller one can't be 1, because if the other one's bigger. Now 2 to the power of k minus 1 has to be greater than 2 squared minus 1, because we said k was greater than or equal to 2. And 2 squared minus 1 is 3. So therefore, 2 to the power of n minus 1 has 2 different factors, and neither of those could be 1. We've shown that both of those is bigger than 1. Therefore, if n is an even number, then 2 to the power of n minus 1 is not a prime number. Now for the contrapositive, that means if 2 to the power of n minus 1 is prime, then n is not even by contraposition. Now, the next type of proof, which we did see last year, but proof by contradiction, reductio ad impossible. So it's an indirect proof. In formal language, that's basically the situation we're talking about here. Because remember, in proof by contradiction, we assume the negation. So what we're saying is, if we have the negation of P implies Q, but then that ends up with a situation where we have both R and not R. So whatever it was we ended up assuming, we end up both true and false, which is of course impossible, then that implies P implies Q. In other words, what we're saying is, if we end up with R and not R, then this can't be true, therefore the other bit must be true, P implies Q. So let's throw that into a truth table to show that, again, that 100% of the time that's going to work. So there's all the possibilities. I can fill in R and not R quite easily, because we know you can't have R and not R. That's just got to be false. Okay, P implies Q over there. Well, the only one that was false was true implies false, so that sorts that one out. Well, negating that will change the truth values, so that becomes false, true, false, false. And now it's this one in the middle here. I've got false implies false, true implies false, false implies false, and false implies false. So we end up with true, false, true, true, which now leads us to matching up the green one here and right over the right, and we end up with them all being true. It's a solid proof. Let's do some. We're going to prove that log 5 base 2 is an irrational number. We'll assume that it's actually rational. So we'll assume the negation of it. In other words, log 5 base 2 can be written as a fraction, P over Q, where P and Q are integers with no common factor, or a way of saying that is co-prime. That means 2 to the power of P on Q is equal to 5. If I play around with the logs there, and then playing around with that, I get 2 to the power of P is equal to 5 to the power of Q. But here's the thing. On the left-hand side, we have 2 to the power of P. So it's just 2 times 2 times 2 times 2 times 2. That's got to be an even number. But on the right-hand side, we've got 5 to the power of Q. 5 times 5 times 5 times 5 times 5. Well, that's got to be an odd number. Hang on. It can't be both odd and even. There's our contradiction. Therefore, we know log 5 base 2 is irrational. You'll notice I didn't write by contradiction there, because I've already mentioned the contradiction in the line before. I mean, it needs to be somewhere in the proof that we've done it by contradiction. I've got it in the second last line this time. We're going to prove that there are no integers a and b such that 18 times a plus 6 times b is equal to 1. That just can't happen. We'll assume the negation of that. So what I'm going to assume is that there does exist a and b, some pair of integers, such that 18a plus 6b is equal to 1. Alright, so 18a plus 6b is equal to 1. If I factorise that and then divide by the 6, I get that 3a plus b is equal to 1/6. But hang on, 3a plus b has to be an integer, because we said a and b were integers. Well, how can 1/6 be an integer? It can't be. No, 3a plus b can't be 1/6. So in one breath I'm saying it is equal to 1/6, but now I'm saying it can't be equal to 1/6. There's the contradiction. So nope. That means there are no integers a and b such that 18a plus 6b is equal to 1. Let's have a look at this one from the 2020 HSC. A set of integers, p is going to be this proposition. If k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. The first thing they said was just prove the proposition is true. You'll notice they didn't say by any particular method. So you can choose any method you like. I said, well, let k plus 1 equal to 3p, p being some integer. Oh, and k, of course, is an integer as well. Well, k cubed plus 1, we have a factorisation for that. But hang on, we just said k plus 1 is 3p. So I could rewrite that as 3p times that second factor. Well, that's 3 times something, and that something is p times k squared minus k plus 1, And that would be an integer because p is an integer, k we said was an integer, so yes, I can write that as 3 times some integer. Thus we've got our proof. If k plus 1 is divisible by 3, k cubed plus 1 must be divisible by 3 as well. The second part said, write down the contrapositive of the proposition. Contrapositive, negate the converse. So it will be, if k cubed plus 1 is not divisible by 3, then k plus 1 is not divisible by 3. Now they asked us to write down the converse of the proposition and state with reasons whether that converse is true or false. The converse is when we read it backwards. So if k plus 1 is divisible by 3, then k plus 1 is divisible by 3. Now, is it true or false? I'm going to use the idea of contrapositive. They've put that idea in my head because of part 2. P implies Q is equivalent to not Q implies not P. Now, P is the statement, k cubed plus 1 is divisible by 3. Q is the statement, k plus 1 is divisible by 3. So let's have a look at that. K cubed plus 1, remember we know it's that factorised. Again, I can write it like that. So if k plus 1 is not divisible by 3, then neither is k plus 1 squared. That's reasonable, right? So we're saying k plus 1 squared is not divisible by 3. Thus, k plus 1 squared minus 3k is not divisible by 3. Why? Well, we just said k plus 1 squared is not divisible by 3. But 3k is divisible by 3, so there's no way we could pull out a common factor of 3 there. Well, that therefore now means the whole thing is not divisible by 3. So if k plus 1 is not divisible by 3, then k cubed plus 1 is not divisible by 3. And now I can use the contrapositive. I say, well, that means if k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3. So that was a nice question in that it got you to look at a couple of different ways of proving things. Alright, that brings us to last year's one. Explain why there is no integer n such that n plus 1 to the power of 41 minus 79n to the power of 40 is equal to 2. Assume then that n, which is an integer of z, that it does happen. n plus 1 to the power of 41 minus 79n to the power of 40 is equal to 2. We're going to assume that's the case. Now, let's look at if n is even, what happens. Then, if n is even, it's fair enough to say n plus 1 is odd. Because we know we go odd, even, odd, even. N to the power of 40 would be even, because n is even. So n to the power of 40 is even. But that also then means that 79n to the power of 40 is even. N plus 1 is odd, so n plus 1 to the power of 41 is odd. We know that. But what we also know is that an odd number minus an even number must give us an odd number. So it can't equal 2. It can't equal 2. So I now got a contradiction. I assumed that it is equal to 2, but I've now shown that it can't equal 2. There's a contradiction. But that's just for even numbers. Now I've got to do it again. Let's see what happens if n is odd. So if n is odd, then n plus 1 would be even. N to the power of 40 would become odd. Well, 79 is an odd number, so 79 times n to the power of 40 would be odd. N plus 1 was even, so n plus 1 to the power of 41 would be even. But now we're saying an even number minus an odd number, which again, that can't be an even number, it's got to be an odd number, so it can't be 2. We have another contradiction. So that means n can't be odd and n can't be even. Well, then it can't be either, so there is no such integer, such that n plus 1 to the power of 41 minus 79n to the power of 40 is equal to 2. They actually really needed to do it twice there to get that one out. Look at the cases 2b and 2c.